Okay, welcome to our second pre-lecture. This one is on the topic of buoyancy. Now, we've seen that pressure varies with depth. That means the deeper you go, the greater the pressure gets to be. And the pressure will be atmospheric pressure plus the density of the fluid times the gravity field times the depth in the fluid. And we're going to use that fact to develop a model for the buoyant force. It'll be on a uniform floating object, but our result will end up being general. Now, we know there's pressure here on the top. If it's floating, then it's exposed to atmospheric pressure. We know that a pressure is a force over an area. So that means the downwards force of air pressure on the top, the air will push in all directions, and it'll push down on the top. It'll also push a little bit on each side, but that'll cancel out. If we solve that for a force, it's a pressure times an area. The corresponding pressure is atmospheric pressure. So that's directed downwards. Now, because we're at depth D in the fluid, the pressure will be greater on the bottom, and we'll call that pressure P. It's still true that a force is going to be a pressure times an area. However, the pressure in this case is given by the expression at the top of the page and is a little bit greater. And this is upwards. Now, if we find the resultant of those two, they're in opposite directions, so we're going to subtract. When we do that, the P naught A's will cancel out, and we'll just be left with this term right here directed upwards. Now, the difference of those two pressure forces is the force of buoyancy. And so we can see it's going to be directed upwards, and it's rho G D A directed upwards. Now, notice here we've got a base area A. Here we are in top view looking down. We assumed it was just a circular object, a cylindrical object. And then D is the depth. So the product of these two things, a base area times a height, is a volume. Now, it is not the entire volume of the object. It's only the amount of the object that's actually submerged. So we can say that a buoyant force is rho GV, but we need to be careful that this volume is not the entire volume of the object, only the volume that's submerged. Another way to describe it is it's the volume of fluid that's been moved out of the way or displaced. So this is a model for buoyancy. You could call it the Archimedes principle for reasons we'll see shortly. And V is the volume displaced. It's going to be equal to, as we saw from elementary mathematics, the cross-sectional area times the submerged depth, D. So that's our model for buoyancy. What we're going to do now is do a couple of examples with that in our pre-lecture here. And then in class we'll look at some demonstrations related to this phenomenon. Let's note first of all, though, that this is often called the principle of Archimedes, and Archimedes expressed the force of buoyancy conceptually. And what he said was that the buoyant force on the object, so let's say this was him taking a bath, the force of buoyancy on him was going to end up equaling the weight of the displaced water. So he imagined freezing the water surface underneath him, and then him getting out of the tub, which would leave a Archimedes-shaped depression in the tub. And then he imagined filling that depression up with water again, so the water surface was again flat and level. Well, because this is clearly an equilibrium situation, and we know that this was an equilibrium situation because he was floating, it must be that the surrounding water here was exerting just as much force as it was in this case, but in this case the surrounding water is supporting the displaced water. So the water that supports him, to summarize, would equally well support the weight of the displaced water. So the force of buoyancy equals the weight of the displaced water. That's the principle of Archimedes. Now we could see that that gives us a similar expression if we solve for a weight of displaced fluid, because starting with the density ratio, if we solve for mass, we cross multiply and see it'll be a density times a volume. And of course a weight is mg, so when we multiply this by g, we get an expression just like we had before, where this is the volume displaced. So that's why we can call the first equation at the bottom of that first slide Archimedes' principle. Because Archimedes said that the buoyant force will equal the weight of the displaced water, and we showed in 2 places that that just equals rho GV. A couple of quick examples then. Let's find the force of buoyancy on a rock sitting at the bottom of a swimming pool. Okay, so here's the swimming pool. There's the water level, and here's the rock. Now let's think first about the forces that act on it. There's going to be 3 things that act on it. First of all, the earth is going to pull straight down. That's a force called gravity. Second, the fluid is going to push up. That's a force called buoyancy. And then because the rock is resting on the bottom of the pool surface will also push up. And once again, that'll just be called normal force. Now I didn't draw the bottom of the pool very level there. Let's just try and fix that a bit. Yeah, because we want these force arrows to be nice and vertical, right? And yeah, it kind of looked like my pool was tilted there a bit. So let's get rid of that pool bottom and make it look nice and square. There we are. Okay, so our force diagram. Getting back to our force diagram, this is the weight of the rock, that's mg. This is the fluid pushing up on the rock, that's a force called buoyancy. And then this is just the normal force from the bottom of the pool, because the rock's sitting on the pool, and so the pool is supporting a bit of its weight. So we can write a force equation. Because the rock's at rest, the forces have to be in equilibrium. So the upwards buoyant force, let's actually write it this way. Just be a bit more formal here. We will call this direction the y direction, and then we're going to say the sum of the forces in the y direction will be the upwards normal force, the upwards buoyant force, and the downwards force of gravity. And the sum of the forces is always the mass times the acceleration, but this side is just 0 since it's at rest. So rearranging, we could say, and you could have just jumped straight to this in a less formal way, you could have said the forces are balanced. The 2 upwards one equals the downwards one. So that's a force equation. Now let's see, we want to find the force of buoyancy. That's good, but this equation is not good because there's 2 unknowns, normal force and mass. So our force analysis hasn't got us where we wanted to go. So let's turn to the Archimedes equation. Archimedes said the buoyant force on an object is rho GV, density of fluid, gravitational field, submerged volume. Now that's going to work because we know the density of pool water. It's 1112 kilograms per cubic meter. We know the Earth's gravitational field is about 9.80 newtons of force for every kilogram. And the volume of the rock, well, we are told that it's a spherical rock. And that means that the volume is going to be 4/3 pi r cubed. 4/3 pi, and then the radius of the rock is 25 centimeters, or 0.25 meters. So I'll just write the formula here for the volume of a sphere, just to remind you, 4/3 pi r cubed. And I'll substitute in now the 0.25 meters all cubed. Now unit-wise, kilograms cancels. The meter needs to be cubed as well as the 0.25, so that would cancel out that meter cubed. And the unit that would survive is newtons. That's good because it's a force. Now let's work out what that force magnitude is. So there we see it's 713 newtons of force. So that's the amount of buoyant force on that rock. Now the weight must clearly be more than that because it's sunk to the bottom of the pool. So that's an example of an object that was had sunk. Now let's do another example where we have a floating object. So here we've got a person who's floating, and they're mostly submerged. Okay, so let's try and draw that. Okay, so here's a person floating in the water, mostly submerged. There we have it. So let's draw the force diagram there. There's only 2 forces acting on this person. There's their weight, the earth pulling down, and then there's the buoyant force, the water, the fresh water, because it's 1,000 kilograms per cubic meter, pushing up. All right, so that's our force diagram. So let's write our force equation then. Forces in the y direction, we'll again take the y direction to be up. I should label these arrows. This is the force of buoyancy from the water. This is the gravitational pull from the Earth. In the y direction, we've got an upwards buoyant force, and we've got a downwards weight. Sum of the forces is always ma, but acceleration 0 because it's at rest. So, and again, we could have just jumped straight to this conclusion in a more sort of straightforward way. The two forces must be balanced. Buoyancy must equal weight. Just let me try scaling this arrow so they look a bit more equal. That's maybe being a bit anal, but hey, that's just the way we are in physics. Okay, so those two forces are equal to each other. Now that, once again, isn't going to enable us to solve the problem because we don't know the mass of the person. So next, let's write an Archimedes equation, because Archimedes, that's horrible handwriting, sorry. Let me try doing it more neatly, because you do need to spell his name. There we go, that's a little neater. Archimedes said that the buoyant force on an object depends on the density of the fluid, the Earth's gravitational field, and the volume that is submerged or displaced for the object. Okay, now this is, well, again, somewhat useful because we know the density of the water, we know the gravitational field. Do we know the submerged volume? Well, the person has a volume of 75 liters, but they're not completely submerged. 5% of them was above, which means 95% of them was submerged. So 95% of their 75 liters. Now, liter is not an SI unit of volume. We will need to convert that to cubic meters. And 1 cubic meter is equal to 1,000 liters. So this is their displacement then. This works out to be 0.075 cubic meters, and 95% of that is under the water. So I can calculate then the force of buoyancy on this person, density of water is given, Earth's gravitational field is known, and then this is 0.95 of the 0.075 cubic meters. And the 0.075 is what results from doing this conversion to cubic meters. So once again, let's see how much that works out to. Okay, and so we could see that works out to 698.25 newtons of force. That's probably too many sig figs, and we'll round that off at the end, but we'll keep it for now. Now, we're asked to find the buoyant force in the person. We're also asked to find the density of the person. So we realize here that there's two densities, and this is going to complicate our lives somewhat. There's the density of the fluid, and the buoyant force depends on that. But then there's, of course, the object, and it's got its density as well. And the density of the object is going to equal the mass of the object over the volume. Now, the mass of the object is not given. So we'll have to find it. The volume of the object is known. We know it's 75 liters. This is the full volume of the object. Okay, so it's not the submerged volume. It's going to be the total volume. Now, we said the mass wasn't known, but we can combine these two previous results and find it because we just worked out the buoyancy. We know from force balance that buoyancy's got to equal mg, so it must be that the mass is just the buoyant force divided by g. Now, we're going to work in SI units, so this is going to be 698.25. Divide that by 9.8, and that'll work out to be kilograms because we've divided newtons by newtons per kilogram. The volume will be 0.075 cubic meters. And if we work that out, it ends up being 950 kilograms per cubic meter is the density of the person. And notice that that is 95% of the water's density, and that is no coincidence. So what we've got then is an equation of the Archimedes principle. This is how to calculate the buoyant force on an object submerged to volume V in a fluid of density rho. We would like to have a definitive answer to the question, when will the object float and when will it sink? We've just done two examples, one where it floats, one where it sinks. How do we know? Well, let's consider a general object, and let's imagine that it's been pushed underneath the water's surface. and then any force that was holding it there has been removed. So now it's been released. And so what happens is going to depend on the magnitude of the buoyant force and the weight. How do those two compare to each other? And there's really three possible cases. Let me just get that vertical again. Okay. And our derivation will actually be general. Okay. Well, actually, we'll have to pick one and derive it. So here's the buoyant force right here. And then here's the weight. So if the buoyant force exceeds the weight, if this arrow is longer, then we've actually had to push it underwater. We let it go. The buoyant force is going to cause it to rise, come out of the water, and sort of like the person, it will displace less water than its entire volume. The buoyant force will get smaller, and then it will stay put. If the buoyant force equals the weight, this is what we call a neutrally buoyant object. Okay, then it'll just stay there. It won't go anywhere. If the buoyant force is less than the weight, in that case we were actually supporting it, like supporting the rock. When you remove that support, the buoyant force is going to be too small to keep it there. It's going to fall down to the bottom. Then there'll be a normal force which will restore equilibrium. So that discusses the three possibilities and how the system will return to equilibrium. Let's just consider one of these for analysis. Let's say it turns out that the buoyant force was greater than the weight, and so this object is going to end up floating. And let's do a little derivation here. And it's going to relate to two densities, because we know that the buoyant force is the density of the fluid times g times the amount of volume that's submerged. But this object is entirely submerged, so that's just the same as the volume v. Now, how about on the other side of the inequality? Well, the mass of that object, we know, since the density of the object will equal its mass over its volume, that I can cross multiply and get an expression for the mass of the object. And I'm just going to skip this line and just substitute this expression for mass on the bottom line. So the density of the object times v times g. So if we've pushed this object underwater, let it go, we know the buoyant force exceeds the weight, it must be true, if the buoyant force exceeds the weight, that this inequality holds. We'll now notice that GV cancels out, and it must be that the fluid density is more than the object density, or, in other words, the object is less dense than the fluid. So the object will float if it's less dense than the fluid. And we've proven this using Archimedes' principle. Now, the other cases are, it'll remain neutrally buoyant if it has the density equal to the fluid, and then it'll sink if it's more dense than the fluid. You could go back and change this sign and do exactly the same steps and arrive at those conclusions. So that's what determines whether an object will sink or float. It has to do with its density. Oh, okay, I see. I had this typed in your book, so hopefully in your notes you had done the derivation right here. So with row object and row fluid being like that, yes, I had that nice spot there for you in the notes, but I missed it here. Anyway, that concludes the derivations for our second class on buoyancy, and we'll pick up this topic further when we meet together.